In the year of 1900, a German scientist named Max Planck proposed a hypothesis that would spark and lead
Hmm.
a new wave of equations and theories to the field of quantum mechanics. He suggested the quantum hypothesis, which theorizes that light energy can only be emitted and absorbed in discrete bundles known as quanta. These packets of energy, known as quanta, is the singular for quantum. Now, if you're having trouble visualizing what packets of energy means, think of a ramp and a set of stairs. Before Max Planck's discovery, energy was represented by a ramp. The potential energy of a person walking up a ramp increased in uniform, continuous manners, which is how energy was assumed to be emitted. However, it was found that energy actually acted more like a set of stairs, where a person walking up the steps in a stepwise quantized manner. Energy came in steps. The reasoning as to why Max Planck had proposed this theory was because he was trying to explain black body radiation. Pause. What's black body radiation, you ask? Well, let's do a quick physics history lesson. Prior to Planck's theory, scientists all over the world were struggling to define what light was. Before Planck, it was mostly believed that light acted as a wave. However, there was speculation that it could have acted like a particle as well. As most of you are also probably aware, objects can radiate energy that fall under an entire range of frequencies on the electromagnetic spectrum. A black body is the ideal representation for a radiating object, and although a pure black body has yet to exist, there is objects that are very close to one, such as coal. Theoretically, they are bodies that can absorb all incoming light without reflecting any, and yet still be able to release energy. The intensity of the energy can be predicted through its temperature, as blackbody radiation is the amount of radiant energy, also heat, emitted at various frequencies for the specific temperatures of a black body. Before the quantum hypothesis was introduced, the basic rules of physics that were accepted was number 1. All matter consists of discrete particles with properties of gravitational mass and electrical charge. Number 2. Light was a continuous electromagnetic wave that traveled at a constant speed, which was later proved to be untrue. And number 3. Continuous electromagnetic fields are created by discrete charged particles. The quantum theory that Planck proposed changed these rules to number 1, that all matter is composed of discrete particles but also wave properties. Number 2, light has discrete particle properties despite also behaving as a wave. Physicists tried to create an equation to prove these set of rules and idea true, but because they considered light as a wave at the time, they ran into many obstacles. The equation they came up with, Rayleigh-Jean's law, theorized that the higher the radiation's frequency, thus a shorter wavelength, would result in a higher intensity of light. However, this theory ran into a large problem, and this period of belief was called the ultraviolet catastrophe, because once the frequencies pass the ultraviolet range in the electromagnetic spectrum, results no longer matched the equation. For black bodies, they were seen to have a peak intensity based on their temperature. At a specific frequency, the light would be at its highest intensity, but past it and the intensity would actually diminish, posing an ultimate problem to scientists and their views on light. As far as they were concerned, a light's intensity and frequency were supposed to be directly proportional. This is where Planck comes in. He was able to solve this problem with his quantum hypothesis. He discovered that the vibrational energy of a solid's atoms was not continuous but had only distinct values. The amount of light energy was dependent on the frequency of the vibration, also symbolized as F, and his theory resulted in the equation E equals n times h times F. E represented energy, n was a whole positive integer, while h was the symbol for Planck's constant, 6.6260 times 10 to the power of negative 34 joules per second. In the journal which he publicized his theory, he states, "Moreover, it is necessary to interpret the total energy of a black body radiator not as a continuous infinitely divisible quantity, but as a discrete quantity composed of an integral number of finite equal parts." He won a Nobel Prize in 1918 for this theory. Using the Boltzmann equation, he suggested that the total energy from black body radiation could be divided into finite parts through a process called quantization. Planck described energy as being made of a finite number of equal parts. There exists a minimum quantity of energy absorbed or released for any frequency of electron oscillation. Planck proposed that heat energy is emitted only in definite amounts called quanta and could not be divided into anything smaller than that. Thus, his equation was first E equals h times F. However, Planck later stated that if at a discrete frequency the oscillation energy exceeds the minimum energy that is emitted, which was represented by the equation E equals h times F, because energy is quantized, every bit of energy that would appear must exist and is limited to n positive whole number multiples of the minimum energy for that frequency. Thus, the equation E equals n times h times F. N has to be an appropriate quantum number. To put that in simpler terms, energy cannot exist between n equals 1 and n equals 2. Energy can only be n equals 1, 2, 3 positive whole integers, never 1.5, 1.8, and those of similar types. And I know, all this information about light and energy can be utterly confusing, with concepts like quantization and quanta that cannot be seen with the naked eye. Concepts like quantization may seem like a confusing, unfamiliar concept, but we actually encounter it in our daily lives. So Canada has gotten rid of its pennies, but we can still use the American exchange currency to show the concept of quantization in our daily lives. US money is integral multiples of pennies. Similarly, musical instruments like a piano or a trumpet can produce only certain musical notes, such as C or F sharp. Because these instruments cannot produce a continuous range of frequencies, their frequencies are quantized. Even electrical charge is quantized. An ion may have a charge of -1 or -2, but never -1.33 electron charges. The hotter an object gets, the more radiation it produces, and black bodies release more energy at specific frequencies compared to others, as seen in Planck's formula. The amount of energy seen through black body radiation is emitted in definite and distinct amounts, thus explaining how black bodies all have a specific peak amount of energy at certain frequencies, and if the frequency is any less or greater, the less energy is released. Little did Planck know that his equation, which he categorized as a fortuitous guess, would contribute so greatly to the worlds of quantum mechanics. Quantum theory, the first evidence that the tiny world of atoms cannot be accurately described with classic physics. This theory became the basis of quantum mechanics, the branch of physics that studies particles at the atomic level and studies its abilities to emit and absorb energy. Planck's theory about light quanta inspired fellow scientist Albert Einstein, and he used it to explain photons and the photoelectric effect mathematically, two ideas that were also significant to quantum mechanics. Einstein showed the quantum hypothesis had a wide application. In 1913, Niels Bohr was the first physicist to use the quantum hypothesis to develop his theory on the structure of an atom and the atomic spectra. He highlighted the relationship between an atom's energy levels and the light frequencies emitted and absorbed by them. In addition, Bohr postulated that an atom would not release energy if it was in a stable state, but only in between levels of stability. The frequency of this radiation would equal the difference in energy between those stable states, divided by Planck's constant. This showed that atoms could not absorb or emit radiation continuously, but only in finite steps called quantum jumps. Planck's quantum hypothesis was the key start to a wide range of subfields under quantum mechanics, such as quantum chromodynamics, the study of the strong interaction, quantum electrodynamics, the study of electromagnetism, quantum electronics, the study of quantum mechanics based on the interactions between electrons and photons, quantum gravitation, the attempt to unify quantum mechanics and general relativity, quantum statistics, the study of particles and statistical mechanics, and various other quantum field theories. The agreement between Planck's theory and several scientists' experiments provided strong evidence that the energy of electron motion in matter is quantized.
So, what are we really made of? Dig deep inside the atom and you'll find tiny particles.
held together by invisible forces. Everything is made up of tiny packets of energy, born in cosmic furnace.